A ship of 10,000 tons is sitting inside a concrete box in the middle of the Panamanian jungle, and the water underneath it is rising. In about 8 minutes it will float 28 feet higher than it did, lifted by water that arrives on its own, out of a lake held back a few hundred feet away, through tunnels wide enough to walk a locomotive through. That is Gatun, the Atlantic staircase of the Panama Canal, 3 chambers, each one 1,000 feet long and 110 feet wide, lifting ocean ships 85 feet from the Caribbean to the surface of a man-made lake. The chambers were finished in 1913, and they still work the same way this morning. To build them, men had to cut a hole down to bedrock in ground that turned to soup every time it rained, place roughly 2 million cubic yards of concrete without a single ready-mix truck, and hang steel gates the height of a 6-story building on hinges expected to stay tight for a century. A contractor handed that job today would reach for hydraulic excavators, concrete pumps, vibrators to settle the pour, and software to sequence the valves. None of that existed. What existed was steam, a railroad, electricity that was still new to most of the country, and about 45,000 people in a place that had already killed tens of thousands before the first American shovel came ashore. So how do you build a machine that size, by hand, in 4 years? If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. The French had gone first. Ferdinand de Lesseps, fresh from his success at Suez, began digging in 1881, with a plan for a sea-level channel cut straight across the isthmus, the same approach that had worked in Egypt. Egypt was flat sand at sea level, with almost no rainfall. Panama was a mountain spine, a river that could rise 30 feet in a night, and a disease environment that nobody yet had the theory to explain. The French company collapsed in 1889. Somewhere near 22,000 workers had died by then, most of them of yellow fever and malaria, and the men who walked away left behind excavating machines that the jungle swallowed within a few seasons. When the Americans took over in 1904, they inherited that record and the reputation attached to it. The first thing that changed was not the digging. William Gorgas, the chief sanitary officer, had watched yellow fever vanish from Havana after Walter Reed's team proved the mosquito carried it, and he pushed the same method onto the isthmus at a cost that made Washington argue for a year. He fumigated buildings block by block, put screens on every window in the labor towns, oiled the standing water, drained ditches, cut brush back from the settlements, and paid men to hunt larvae in cisterns and cemetery urns. Yellow fever was gone from the isthmus by 1906. Malaria never left, but it stopped emptying the camps, and that is the reason there is a lock at Gatun at all. Concrete work runs for years without stopping, and years without stopping requires a workforce that is not dying faster than it can be replaced. That workforce came mostly from the Caribbean. Recruiters worked Barbados hardest, and Barbadian men became the largest single group on the isthmus, alongside thousands from Jamaica, Martinique, and Guadeloupe. Spain, Italy, and Greece supplied crews for the heavy concrete work at the lock sites. The Americans running the project sorted everyone onto 2 payrolls. The gold roll was paid in United States gold, held the engineering and supervisory and skilled positions, and was almost entirely white and American. The silver roll was paid in Panamanian silver, held nearly all of the manual labor, and was overwhelmingly West Indian. Separate housing, separate mess halls, separate hospital wards. The men who mixed and placed most of the concrete at Gatun were on the silver roll, and their names went into the record with far less care than the tonnage they moved. The lock site itself was chosen for what sat underneath it. Instead of building in the soft floodplain of the Chagres River, the engineers set the locks into a shoulder of rock on the east side of the valley, where the foundation could be trusted to carry the load without settling. Steam shovels stripped the hill. Bucyrus machines weighing 95 tons bit into the cut and swung their dippers over, waiting flat cars, and the spoil went out on the Panama Railroad, which had been relaid and rebuilt specifically to carry that traffic. 2 pieces of equipment made the haul work at scale. The first was an unloading plow, A steel blade dragged the length of a loaded train by a cable and a winch, which scraped an entire string of cars clean in a few minutes, instead of the hours it would have taken a gang with shovels. The second was the track shifter, a crane-like machine that lifted an entire line of rail and ties and set it down several feet to one side, so a dump line could be moved by a small crew in an afternoon rather than torn up and rebuilt by hundreds of men. The material coming out of that hill did not go to waste. Much of it went into the great earth dam across the Chagres, the structure that drowned the valley and made the lake the locks were built to reach. 2 million cubic yards of concrete is the number that stops people. There was no plant on earth that could deliver that much finished concrete, so one was built on the bank. Crushed rock came by barge from a quarry at Portobelo, about 20 miles up the coast, and sand came from Nombre de Dios nearby. Both landed at a dock and lifted into storage bins by bucket conveyor. Portland cement arrived from the United States by the shipload, more than 4 million barrels of it for the canal as a whole, and moved down to the site by rail. Water came from the river. Mixers charged from the bins turned out batches around the clock, and the batches went into buckets of 2 cubic yards, weighing close to 6 tons when full. Getting those buckets over the work is where the ingenuity lives. 2 cableways spanned the entire lock site, strung between steel towers 85 feet tall that stood on parallel tracks about 800 feet apart and rolled forward as the walls advanced. A loaded bucket was hooked onto the carriage, run out along the cable over open space, stopped above the right section of form, and lowered on signal. The operator sat in a cab hundreds of feet from the pour. He could not see into the form. He set that 6-ton bucket down by watching a man on the wall who worked a vocabulary of arm signals, the same way steel gangs in New York were placing beams in the same years, and he judged the last few feet by feel and memory. A bucket dropped hard enough could shift a form or kill a man standing in it. The forms were steel, built in sections and reused down the length of the wall, with curved shells for the culverts and shaped panels for the recesses that the gates would fold into. Carpenters and steel setters worked ahead of the pour, bolting the next section into position while the previous one was still being filled behind them. Placing the concrete was handwork all the way. There were no vibrators. Men stood in the wet mix in rubber boots and worked it with shovels and long steel rods, ramming it against the face of the form and around the culvert shells to drive the air out. A pocket of trapped air at the face becomes a void, and a void in a lock wall becomes a leak that no one can reach again once the chamber is flooded. Between one lift and the next, the surface was scrubbed with wire brooms, washed down and coated with cement grout so the new concrete would bond to the old. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The walls carry the water by weight alone, with no reinforcing steel through the mass of them. The side walls are roughly 45 to 50 feet thick at the base and taper to about 8 feet at the top. The center wall, shared by the 2 lanes, is 60 feet thick, and it is not solid. Inside it run culverts, passageways, stairwells, and a tunnel that let crews walk the length of the locks below the waterline. First concrete at Gatun went down in August of 1909. The last of it was placed in May of 1913, day shift and night shift, through 4 wet seasons. Everything described so far is the container. The machine is the water system buried inside it. Running the full length of each side wall and the center wall is a culvert 18 feet in diameter, large enough for a work crew to walk through upright with room over their heads. From those main culverts, cross culverts branch out under the floor of each chamber, and each of those opens through a row of holes in the floor itself, something close to 70 openings in a single chamber. Water enters from below and from everywhere at once, so a ship comes up on a rising flat surface instead of being shoved around by a current. Roller valves inside the culverts control the whole thing. Open the valves between a higher chamber and a lower one, and gravity moves about 26 million gallons from one to the other, and when a ship steps back down toward the sea, that water runs out to the ocean and is gone. No pump has ever lifted a ship at Gatun. The gates are the pieces that make people stop on the observation deck and stare. They were fabricated by McClintock Marshall in Pittsburgh, shipped in pieces by sea to Colon, hauled to the site by rail, and assembled leaf by leaf on the dry floor of the chambers, riveted plate to plate with pneumatic hammers, the same trade and the same tools that were putting up the skyscrapers of Manhattan in those years. Each leaf is 65 feet wide and 7 feet thick, and depending on where it stands in the flight, somewhere between 47 and 82 feet tall. The tallest weigh several hundred tons apiece. They are also hollow. The lower portion of each leaf is sealed as an air chamber, so the leaf floats against part of its own weight and takes load off the pintle it turns on at the bottom. When the two leaves swing shut, they do not meet in a straight line. They close at an angle pointing upstream, so the pressure of the water behind them forces the joint tighter rather than pushing it open, an arrangement borrowed from European canal builders working 4 centuries earlier. Each leaf was driven by a bull wheel, a gear ring 19.5 feet across, set half into the lock wall and turned by an electric motor, connected to the gate by a steel arm that pushed and pulled it through its arc. Power came from a hydroelectric station at the spillway of the new dam, so the locks ran on the same river they were built to hold back. Sequencing all of that fell to one man in a control house standing over a working model of the lock, brass and steel, laid out to scale, with a lever for every gate and every valve, and an indicator that moved only when the real gate or the real valve moved out on the wall. Interlocks built into the board made it physically impossible to pull the levers in a wrong order. An operator could not open a gate against a head of water, could not open the wrong valve, could not empty a chamber that still had a gate standing open. That was mechanical logic, cut in metal decades before anyone had a computer to do it. The ships themselves were held off the walls by towing locomotives built by General Electric, running on a rack rail along the top of each wall and taking the vessel on wire ropes, keeping it centered in a chamber with only 2 feet of clearance on either side of some hulls. Every point in the flight where a failure would have emptied the lake was given a second set of gates behind the first, a spare barrier standing idle for decades on the chance that the working one gave way. At the top of the staircase, the builders went further and installed emergency dams, steel trusses on pivots that could be swung out over the channel and let down in sections to choke off the flow of an entire lake. They were never used. Decades later, they were taken out and scrapped. A ship still climbs the 3 chambers in about an hour and a half. The cost of all this was paid in the usual currency. More than 5,600 deaths were recorded during the American construction years, and the great majority of them were West Indian workers on the Silver Roll. Disease took most, the rest came from the work itself, which at a lock site meant falls from forms and staging, crushing under swinging buckets and setting steel, blasting accidents at the quarries that fed the mixers, and pneumonia that ran through crowded barracks in the wet season. The quarry crews at Portobelo drilled and shot rock by hand and loaded it onto barges in open water. The men who worked the cableway towers spent their shifts on steel, 85 feet in the air, the same exposure the New York ironworkers had in the same years, and the same absence of anything resembling a harness. Men who lived outside the labor towns, in the villages along the line, often died outside the records altogether. The engineering triumph and the burial ground are the same project, and the men who carried it were not commemorated with anything close to the care given to the men who designed it. The canal opened on the 15th of August 1914, and the world barely looked up because Europe had gone to war 2 weeks earlier. What was built at Gatun outlasted the news. The chambers poured by hand between 1909 and 1913 are the same chambers working today, more than a century of salt water, tropical heat, and constant loading later. Many of the original gate leaves are still swinging, repaired and repainted but not replaced. The bull wheels finally came out around the turn of this century, swapped for hydraulic struts that do the same job with fewer moving parts. In 2016, a second, larger set of locks opened alongside the old ones, with rolling gates that slide sideways into pockets, tugboats instead of towing locomotives, and basins that catch and recycle a share of the water rather than sending it all to the sea. The new locks are better in every measurable way, and they were built with machines the men at Gatun could not have imagined. And the old staircase still runs beside them, filling from below through 18-foot culverts, lifting a ship 85 feet on nothing but the weight of the water above it, exactly as it was arranged by a few thousand men standing knee-deep in wet concrete with steel rods in their hands. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.